So as said, in this video we'll talk about how to calculate the noise of a question. Okay, this is question 4 of a certain exam question. So an op-amp has a noise performance quoted as 12 nanovolt. Okay, so 12 nanovolt means that it is 12 times 10 to the negative 9. Okay, it is to be used in a circuit amplifying signals in frequency range of 50 Hz to 75 kHz. Okay, the op-amp is said to have a gain of 200 gain. Calculate the level of noise output by the op-amp in this situation. Okay, if the signal input is the op-amp has amplitude of 1 millivolt, what will be the signal to noise ratio? And your answer should be shown as both ratio and then as decibels. And then you comment on this ratio. Okay, so let's do it. So the first thing, if you remember previously, we have to first find the range. So 75,000 minus 50 equals to so 75,000 minus 50 equals to this value. Right, and then I square root this thing. Okay, I square root. Wait, I cannot do that. Fine. 74950. I'll have 273.7699. Right. So I have 273.7699. Right. This is calculate frequency range. After I calculate my frequency range, the next step I need to do is actually to calculate my input noise. Alright, my input noise. So my input noise is actually 12 times 10 to the negative 9, right, times the frequency range, which is this value 273.7699. What do I have? Right, so I have in this case 12 times 10 to the power, what is my power? To the negative 9, right? And then I multiply with where am I? 273.7699. Okay, 273.7699. I have, wow. So 1, 2, 3, 4, 5, 6. So I have 3.28. 3.28 noon, what's that called, volt, right, 28523 28523. Okay, so yeah, and then after that, the next thing I need to do is actually to calculate the output. So this is the input noise. So now I have to calculate the output noise. I'll be taking 3.28533 times 10 to the power negative 6 multiplied by the gain of 200. If they give you decibels, okay, whatever. So I already calculated in the last video how to change to decibel to gain. So in this case it's gain. So if you were to multiply times 200, okay, so I multiply by, where am I? So this value, if I multiply by 200, I'll have 1, 2, 3, 4, 6.57. I'll have 6.57 times 10 to the negative 4 volt. Right? Yeah. So next what I'm gonna calculate is the ratio. So my ratio is what my ratio is. My ratio is 1 millivolt, right? So my ratio from my input signal over the noise lah, okay. Actually should be output signal lah. Input and output signal, if it was a clean one, it will be the same, and then divided by output noise. So 1 times 10 to the power of negative 3, 6.57 times 10 to the negative 4. Then you will get 1 divided by 6.57. What do you have? So let's calculate. 1 divided by 6.5. Now equal 6.57. You have 0.1522. So you have 0.1522 times 10, right? Negative 3 divided by negative, that means minus 4, you have equals to 1, right? So you have 1.522 ratio. Okay, so this is the ratio already. My thought before I go into this step, right? Maybe I should remove all this first. Okay, why is it? Okay, this is a step that this exercise didn't show. Alright, because input noise times gain is equals to this one, right? Input noise times gain is equals to this. However, it didn't multiply with the gain of 40 decibels. It didn't multiply. So there's no gain at all. So in this case, if you have a gain, in this case you have to multiply your input noise with your input signal has to multiply with gain times gain, which is 0.1. In this case is 1 milliamp. Yeah, 1 milliamp is this one, right? This is your input signal. 1 times 10 to the negative 3 times 200. You'll get 200 times 10 to the negative 3. So after which I can then compare with my so output signal divided by output noise, right? So take note that if you have a gain, make sure you put in the gain, okay? In this case, there is a gain of 40 decibels. However, they didn't. Oh, they actually switch words. Output voltage is 0 decibels. So output voltage. So they already straight away put the output voltage already. Output noise. Okay. So in this case, as you can see, this is the signal input. Okay, signal input. So you have to also find your signal output. In this case, they already give in the previous example case, they already give you a signal output already. So this is why, yeah, it's a very important thing. And then, yeah, so with this thing, so this is all output signal divided by output noise. So you have to remember this formula, the output signal divided by output noise. So if I were to do that, 200 divided by 6.7, 200 divided by 6.57, 30.44. Okay, great job. Why? Okay, on the right track. I have to constantly check with the answer before I go wrong. So 30.44 times 10, because 10 to the negative 3 minus 4, you have plus 4, right? This is just this portion over here lah. So I have 304, right? This is the ratio. So they say that you have to transform it into a decibel point, right? So in order to transform decibels, what I'm gonna do is actually do 20 log 304. Right, so 20 log 304, what do I have? So I have 304 first. And then where's my logarithm? I have no logarithm, good job. I use Google calculator, so log, sorry, my fault. Okay, so 20 log 304, right? I have 49.657, right? 49.657 dB. So this is my decibels. So you want to comment on this. So comment, I also don't know how to comment. So let's go to the answer sheet and then you will know how to comment. So as from the answer, you can see that it's 49.6 decibels, okay, which is approximately the same as my 49.657 decibels. Okay, the range is about there, right? So this is how I translate it into there. So I'm not going to go through this anymore. So the signal is to noise ratio is quite small and therefore not ideal. Okay, why not ideal? Frankly, I don't know why the signal to noise ratio is quite small. Yeah, I searched for a long time. 1 millivolt, okay, if you take input signal as 1 millivolt, compare with 12 nanovolt input noise, right? The difference is actually quite big if you were to do a signal input divided by input noise. Right, the ratio will be, because 1 milli divided by negative 3 divided by negative 9, you have 600,000, which is not small at all. You see, the signal to noise ratio is quite small. Where is quite small? I don't see quite small. I don't know, I may be wrong, I don't know. And then it's therefore not ideal. I don't know how. And then, however, the signal is 300 times greater than the noise. Right, this can be seen from over here. The ratio 200 divided by 0.66 is about 303 times. So at least is acceptable lah. And there is no range in the text to tell you whether is it acceptable or not. So if it's above 100, I think or whatever you just anyhow whack lah. Let's say that okay, acceptable. Why acceptable? Because 300 times, so better lah, If it's like maybe like 2 or 3 times, and then that definitely is not stable. I mean acceptable. In this case, I have no idea what the hell is this thing. Okay, I have no idea what is this thing. Okay, and then yeah. So I'll just call it a day for this one. Okay, so I have answered all your answers on op-amps. Alright, so in the next series of the video, I will go on to a little on sensors, a little on ammeter, voltmeter, and multimeter, and then capacitance, I don't know what, chapter 9, IDS, how to, yeah, and then a little calculations and such. So in the next series, I'll talk about the things that I haven't talked about it yet. So I'll see you in the next series. Goodbye.